Hello again and welcome back to our video training series on power system protection. Even if the protective relays, breakers, CTs, VTs, and communication equipment all seem to work exactly as planned, our job is not complete. We still need to investigate each disturbance after the fact. But why is it necessary to go back and analyze faults after they happen? Well, this is done for two basic reasons. First, to check that the relays and breakers are operating as intended, and second, to explain any misoperations and predict any future problems. Protective relays and breakers operate extremely fast. They can clear a fault in just a fraction of a second. Unless we can capture fault data and reconstruct what happened during that very short time frame, we would probably never be able to pinpoint the cause of relay or breaker misoperation. Furthermore, even if the protection seems to operate correctly, there could be problems that would go unnoticed if an after-the-fact analysis is not conducted. Here's an example that shows why every fault on the system should be investigated. In this simplified one-line diagram, a high-voltage 500 kV transmission system is connected to a 161 kV sub-transmission system through substation X. The YY transformer is equipped with CTs in the grounded neutral leads on both the high-voltage and low-voltage sides. The CT secondaries are then connected in parallel so as to monitor the total ground fault current from both the 500 kV and 161 kV systems. The current monitored by this CT arrangement is referred to as the station neutral ground current. A single line-to-ground fault occurred on C phase of one of the 161 kV lines leaving station X. These traces were recorded automatically by an oscillograph machine installed to capture fault information. Here we show the C phase current on the faulted line and the station neutral current. Just prior to the fault, normal load current flows in C phase of the line, and the station neutral current is close to zero. When the fault occurs, both phase current and neutral current increase dramatically, as we would expect. After about 5 cycles, breaker number 1, protecting the faulted line, trips to clear the fault. There are about 30 cycles of line dead time before breaker number 1 recloses. Like most faults on overhead lines, this one was transient in nature. It was probably caused by insulator flashover from a lightning surge, or perhaps high winds momentarily pushing a tree branch into the conductor. 30 cycles of dead time with no current flowing is usually sufficient to allow the fault arc to deionize. So when the breaker reclosed, it did not trip out again. You can see from the trace that breaker number 1 has successfully reclosed. So far, the line protection has operated exactly as we would expect. But take a look at the station neutral current. It is extremely distorted and became progressively worse during the 5 cycles that the fault was on. Distortion like this is a clear indication of CT saturation. In this case, the saturation is caused by the fact that the fault current is not symmetrical. There is much more negative magnitude than positive. This offset in the fault current is called DC offset, and it has the same effect as adding burden to a CT. The CT secondary output becomes distorted and no longer accurately reflects conditions on the system. Now, you'll remember we discussed this problem in PSP 3, but you might say, if the protection worked okay, why should we worry? Well, the problem is that the same pair of CTs are also used to provide polarizing current for the directional relays on the line. This current is used as a reference to determine whether a particular fault is in the tripping or non-tripping direction. The direction of polarizing current is compared with the direction of current flow in the line. In this particular incident, the relays associated with breakers 2 and 3 on the 500 kV system registered the high current, but decided that the fault was in the non-trip direction. Carrier block signals were then sent to block tripping of the remote breakers. This is correct. The problem of CT saturation was noted on the fault analysis report for future consideration. Sure enough, a few months later, a similar fault occurred on the 161 kV system, but this time the 500 kV breakers tripped incorrectly before the 161 kV breaker could clear the fault. Here are traces of the carrier signal that was transmitted from breaker number 2 during the fault and the C-phase current seen by breaker 2. About 3 cycles into the fault, interruptions or holes begin to appear in the carrier signal. The holes are due to the extreme distortion in the station neutral current, that is, the reference current. How is this? Well, when the relays at breakers 2 and 3 compare the ground residual current with the distorted reference current, the phase relationship is unclear. The relays now mistakenly decide that the fault is in the trip direction and simultaneously suppress the carrier blocking signal. This allows the breakers on the 500 kV system to falsely trip for a fault on the 161 kV system. As before, this was a temporary fault, so all breakers reclosed successfully at high speed. The problem was solved by replacing the 161 kV neutral CT with one having better operating characteristics. There are 2 basic methods for gathering fault data: automatic and manual. Fault data is recorded automatically on oscillograph machines and sequence of events recorders. An oscillograph machine starts automatically when a fault occurs. It records waveforms of selected voltages, currents, and communication signals. On the other hand, a sequence of events recorder constantly monitors the status of control switches, breaker contacts, and relay contacts. Whenever a change in status occurs, the device number and the status change are printed out as a typewritten list. These automatic recording tools will be described in more detail in the next segment. Fault data can also be gathered manually. This is done by checking and logging the operation of protective relays. As you know, each relay is equipped with a brightly colored target or flag that tells us when the relay has indeed operated. Such relay actions are always logged for future reference and analysis. Indeed, on distribution systems, this is often the only information which will be available to assist analysis. Here is one example of a relay action log which reports upon failure of a lightning arrestor during a lightning storm. The failed arrestor was located on the low voltage side of a 115 to 69 kV auto transformer. The resulting fault within the transformer's zone of protection caused the differential relay to operate. This in turn tripped all 3 breakers, primary, secondary, and tertiary, to completely isolate the fault. The actual information logged includes the date and time of the relay action, the numbers of the breakers involved, the relay targets, the time each breaker was closed, and the number of the pertinent oscillograph recording. In this particular case, the investigator, using all of the data along with the oscillograph traces, decided that all relay and breaker actions were correct. This is noted on the form. Any misoperations would typically be reported on a separate log, and a thorough investigation would follow. Of course, these relay action reporting procedures will vary from utility to utility, so you must be sure to check and learn your own company procedures. At this point, it's time for a break. In the next segment, we'll be looking at fault analysis tools in more detail. Until then, please switch off the videotape and review the written material in your workbook. In this segment, we'll be looking at the most common analysis tools which are used to investigate faults and other disturbances on the power system. These are oscillographs, system one-line diagrams, sequence of events recorders, relay targets, DC schematic diagrams. By correlating the one-line diagram with the oscillograph traces, we can usually reconstruct what happened and consequently analyze the fault. We may then verify our findings by checking the printout from a sequence of events recorder, also known as an SER. The SER may be an integral part of the oscillograph system, but quite often it is a standalone machine. This type of recorder is capable of monitoring 1,000 input points. For example, breaker open or closed status, breaker trip coil status, relay operations, transformer and generator alarms, and so on. The SER is constantly monitoring the status of each input point and prints out a detailed record whenever the status changes. A typical SER printout gives the exact time of the event down to the millisecond. It can distinguish between two events occurring 1 millisecond apart. It provides a plain language description of the event, the identification number of the input point, and an A or N code indicating whether the status of the device became abnormal or normal. In some installations, instead of a specific SER, the status is monitored by telemetering, that is, the SCADA system. Another tool we need to use in fault investigation is information regarding relay targets, which is usually logged by operators. Like the SER output, these logs are normally used to verify and support the conclusions drawn by examining the oscillograph records. However, in some cases, relay target and SER data have provided the missing link in solving problems due to disturbances. Now, let's take a closer look at the oscillograph machine. There are 4 oscillograph systems in widespread use on the power system today. These are referred to as quick start, pre-fault, continuous, and digital. The quick start oscillograph is the simplest type and uses a high-speed recorder. As soon as a fault is sensed by a protective relay or other sensor, the machine starts and the paper begins to move after 3 or 4 milliseconds. Of course, this presents a problem since the data at the very beginning of the fault is lost. The loss amounts to about 1/4 cycle of data. Also, there is no way of capturing the conditions on the system just prior to the fault. In spite of these disadvantages, many users prefer the quick start system. They are willing to live with some data loss in exchange for the simplicity of the machines. Another type of recording system uses a pre-fault oscillograph. This machine has a built-in solid-state memory that can store several cycles of data, up to 30 cycles in some machines. The memory works in a recirculating fashion. For example, at any instant in time, the memory stores the immediately preceding 30 cycles of data. As time goes on, the memory is constantly storing new data while dumping old data. But there's always 30 cycles of data in storage at any given time. Now, when a fault is sensed, the machine begins printing out the 30 cycles of pre-fault information it has stored in memory. While this is being recorded, the fault information is being inserted into memory. By the time the actual fault data starts recording, the machine is fully up to speed. This results in a very clear transition between no fault and fault conditions. Because of the recirculating memory, no data is lost. A third type of fault recording machine is the continuous oscillograph. In contrast to the quick start and pre-fault recorders, this machine does not need to be started by a fault or disturbance, and it also does not use paper. Instead, it continuously records system conditions on reusable magnetic tape. When a fault occurs, we can save about 6 hours of data by initiating a save command. This can be done automatically by protective relays or other sensors immediately after a fault is detected. Data can also be saved manually by a remote switch on the operator's console. Since data is continuously being recorded, the operator can decide to save information after the disturbance has occurred. Once the data is saved on magnetic tape, we can get a hard copy printout of the waveforms for analysis. In addition to the oscillograph machines themselves, there are several accessories that must be installed to complete the recording system. And these include starting sensors or triggers to start the recordings, signal conditioners to prepare the data for recording, power supplies and inverters to provide an uninterruptible power source for the oscillographs, and time clocks to keep track of the exact time of recording. The time log helps coordinate the output from many recorders. The most important accessory is the starting sensor. The sensor is basically a relay which continuously monitors the power system and detects disturbances such as faults and power swings. The sensor signals an oscillograph machine to start recording. Fault sensors are the most common type. Now, they typically respond to overcurrent or under voltage. For example, this overcurrent sensor in the neutral circuit of a transformer detects single line-to-ground faults out on the system. Often this sensor is backed up by a zero-sequence voltage sensor connected across the broken delta winding of a voltage transformer. This measured voltage is zero under normal conditions, but it greatly increases for a line-to-ground fault. Thus, we can set the voltage sensor very sensitively to provide good backup for the current sensor. We can also use a negative sequence voltage sensor connected to the bus. This will sense a phase-to-phase fault on any line connected to the bus. You will remember this phasor diagram from an earlier lesson. It shows the voltage broken down into its positive and negative sequence voltages. Before the fault, we have balanced three-phase voltages. The negative sequence component is zero. As soon as the fault is applied between A and B phases, the negative sequence voltage suddenly increases. So when this sensor detects negative sequence voltage, we can be quite sure that a fault has occurred and recording can begin. Another type of sensor, the disturbance sensor, responds to slower changes in voltage, current, or even system frequency. These slower changes take place over many cycles and are commonly called system swings, instability, or oscillations. Oscillographs do have their limitations. For example, a lightning surge would not be recorded because it's much too fast. A typical current surge due to a lightning strike reaches its peak and decays to zero in a matter of microseconds. Although our conventional recording machines could not pick up the actual surge, we may be able to see the effect of the lightning. This trace shows B phase to neutral voltage on a transmission line during a lightning storm. Look carefully at these points. Here, we see the high-frequency effects of arresters operating and conducting surge current to ground. Subsequently, at this point, the high voltage associated with the lightning surge flashed over the line insulators, creating a temporary phase-to-ground fault. You can see the dramatic decrease in voltage due to the fault. This particular recording was started automatically when the fault occurred and captured about 5 cycles of pre-fault data. Because of the pre-fault capability, we can see the effect of the lightning arresters. But take note, the recording would not have started at all if a fault had not subsequently developed. This is because the sensors can only detect longer-term disturbances in the range of milliseconds or seconds. A normal arrestor discharge without a fault is too fast to be picked up by the sensors, so it would not start the recorder. We have been looking at oscillograms associated with faults on the system. Generally, the whole story can be shown within a few cycles, usually less than 1 second. System swings, such as those associated with instability, can also be recorded, but such swings may last for several hundreds of cycles and consequently give us a lot of paper to examine. Some oscillographs have the ability to change paper speed automatically when recording these longer-term swings. In recent years, most of the fault analysis systems installed are of the digital type, generally known as digital fault recorders. This type of system usually allows for a greater number of monitoring inputs. The measurement, that is, sampling, is made simultaneously from all inputs, and a very high rate of sampling is achieved, say 6,000 measurements per second. The analog input is converted through an AD converter into a digital signal to be recorded in the memory of the recorder. The information can be viewed on the computer screen or printed out as required. Usually, the screen traces can be compressed or expanded in both time and amplitude so that a variety of signals can be compared. For precise examination, the curves can be overlapped. A distinctive advantage is the capability for immediate remote retrieval. Information from various locations can be brought into a master computer for analysis at a central location. In this context, another advantage is in the precise timekeeping of the digital system. Yet another advantage is the capability to adjust the individual trigger set points from remote central control. In some digital systems, a printout of equipment status can be produced similar to the SER. As further development takes place, it is probable that gathered information will be analyzed instantaneously by the computer and switching operations initiated. Keep your eye open for such developments on your power system. So up to this point, we've discussed what types of oscillograph machines are installed, what sensors start the machines, and what types of disturbances they can record. Now, let's consider where on the power system these machines may be located. Obviously, we cannot locate the recorders at every substation. The cost would be too great. As a general rule, most utilities find that they can adequately monitor the system by installing recording machines at every station in the extra high voltage range, that is 345 kV and above, every other station in the high voltage range, such as 115 kV and 230 kV. This allows at least one end of each high voltage line to be monitored. Every major generating station, and every station with interconnections to other systems. Normally, oscillographs are not located at the distribution substations except those installed to analyze special problems or to conduct research. But it is just as important to analyze incidents occurring on the distribution system as on the high-voltage power system, even though you may not have the help of sophisticated recording equipment. In this area, you will have to rely upon operating reports, including relay target data. Well, now it's time for a break. In the next segment, we'll be taking a closer look at the recordings themselves, that is, the oscillograms, and show how they can be used in fault investigations. For now, please turn off the videotape and consult your workbook. The oscillogram is probably the single most important tool for analyzing faults on the power system. Just what can we tell from this collection of wiggles on a piece of paper or on a computer screen? Well, very quickly, we can deduce what type of fault occurred. Phase to ground, phase to phase, and so on. What phases were involved, and whether or not the breakers and relays operated correctly. Now, just how much system data do we need in order to make a proper diagnosis of system faults and other disturbances? First, you should recognize that we cannot monitor every voltage and current in a particular installation. Many older recorders are limited to 32 channels of information. New digital machines allow 64 channels or even more. Either way, the precise data to be monitored must be carefully selected to get the maximum amount of information after a fault has occurred. At this transmission substation, for example, some of the more important quantities to monitor are bus voltage between each phase and neutral, line current in at least one phase, line residual current, transformer neutral current, and received carrier signals for each line. Let's look at each of these quantities and see why they are important in analyzing faults. Bus voltages are important because they can usually tell us what type of fault has occurred. Low voltage on one phase indicates a single line-to-ground fault somewhere on the system. Two low voltages can mean a line-to-line or double line-to-ground fault. Three low voltages indicate a three-phase fault. We can sometimes save on channels by routing three voltages, A phase, B phase, and C phase, all to one channel. This is called multiphasing or multi-channeling of the voltages. It is done by feeding the measured three-phase voltages to a rectifier circuit. The output voltage of the rectifier consists of just the peaks of the voltages in each phase, and this is what is printed on the oscillogram. The scaling which represents voltage is different for each phase, so that we can easily differentiate. In this trace, the A phase appears to have the highest peak, followed by B, then C. As a matter of fact, this oscillogram shows the incidence of a fault. Look here, the B voltage has decreased, while A and C remain normal. Multiphasing comes in handy when we wish to monitor voltages on individual lines in addition to the bus voltage. A common arrangement would be to use a separate channel for each phase to neutral bus voltage, and then multi-phase selected line voltages. It's also important to look at phase current in each transmission line. The current traces can then be compared with voltage traces to confirm which phase or phases were faulted. A sharp rise in current and drop in voltage on A phase, for example, is a pretty sure sign of an A phase fault. Often there are not enough channels to monitor each phase current of every important line. So, quite often, only one phase of each line is monitored, with the phases alternating from one line to another. However, every major transmission line should have its residual current monitored. Where CTs are Y-connected like this, we can conveniently measure residual current or 3I0 current in the neutral return circuit. These are the same CTs that provide input to the protective relays for line protection. As you know, the residual current, IR, is the phasor sum of the three-phase currents. Normally, it is very close to zero. But when a line-to-ground fault occurs, this current becomes very large. You will often see the residual current expressed as 3I0. Remember, the magnitude of current for a single line-to-ground fault is just 3 times its zero-sequence component. Another very sure way of detecting ground faults is to monitor the current in the grounded neutral of a Y-connected transformer winding. Again, this current is quite small under normal, balanced conditions, but rises significantly when a ground fault occurs. Another important quantity to measure is the carrier signal, which may either block or initiate tripping. Typically, just the received signal is monitored for each line. This signal may be generated locally or at the far end of the line. With this information, we can often spot the cause of relay and breaker misoperations during faults. Here's an example of how we can use oscillograms to quickly diagnose a fault condition. This substation has 2 lines connected to a common bus, and various voltage and current transformers are installed. Line 1 becomes faulted, and this starts the oscillograph recording the following traces: bus voltages in each phase, line current in each phase of line 1, the station neutral current, and received carrier signals on both line 1 and line 2. What can we immediately tell from these plots? Number 1, the fault was a single line-to-ground fault on the A phase of line 1. We know this from the depressed A phase voltage at the substation bus. The other bus voltages are normal. Also, the A phase line current undergoes a sharp rise, while the other phase currents are unaffected. Finally, the station neutral current also increases from almost nothing to a large value. This indicates a line-to-ground fault. Number 2, the fault cleared in about 4 cycles. After 4 cycles, the A phase bus voltage is back to normal, and all 3 line currents plus the neutral current go to 0. This tells us that the line has tripped out of service at both ends. Number 3, the line reclosed successfully after 20 cycles of dead time. This is obvious from the resumption of load current. Notice that the local breaker X closes first, and the remote breaker Y closes about 2 cycles later. During this period, the line is energized from one end only. The small current flowing is due to line charging. After the remote breaker closes, load current again flows. Number 4, only the faulted line has tripped. We can tell this from the received carrier signals on lines 1 and 2. Since this is a carrier blocking scheme, a received signal means that high-speed tripping is blocked. You can see that the system operated correctly. The unfaulted line 2 breaker receives a blocking signal, while the faulted line 1 breakers receive no signal. This allows line 1 breakers to trip at high speed and clear the fault. This example has demonstrated a case where the protection system worked exactly as we expected. The role of the oscillograms was to confirm this fact. Here's an example of how oscillograms, along with some computer simulations, can help pinpoint the location of trouble areas along a transmission line. The system one-line diagram shows two substations, A and B, separated by 100 miles of line. Both stations are equipped with oscillographs that monitor transformer neutral currents, INA and INB. This installation suffers a particular problem. The line trips and recloses on a recurring basis. The faults seem to occur whenever the line is heavily loaded and wind velocities are above normal. This leads us to believe that the line is sagging under heavy load and making tree contact. But we have no idea where the problem is located. We can prepare for our investigation by first running a series of simulations using a short-circuit computer program. First, we assume that a fault occurs at various points along the line, say 20 miles, 40 miles, 60 miles, and 80 miles. For each different location, the computer program calculates a ratio, INA divided by the sum of INA and INB. This ratio represents the fault current contribution from station A divided by the total fault current. When the fault current ratio is plotted against fault location in miles, we get a series of points and a curve that looks like this. If the fault is very close to station A, INB will be quite small compared to INA, so the ratio will be close to 1. On the other hand, if the fault is close to station B, INA will be small and the ratio will be close to 0. For a fault near the middle of the line, INA and INB will be about the same, so our ratio is close to 1/2. Of course, we can create a whole family of curves for different system conditions, such as maximum generation and partial generation. Now that we have the simulation curve, how are the oscillograms used? Well, after a fault occurs on the line, the oscillograms are checked, and the magnitude of neutral current in each station is read from the plots. For this particular fault, INA is 1,500 amps, while INB is 4,000 amps. Our fault current ratio is 1,500 divided by 5,500. This works out to be 0.27. Now, going back to our computer simulations, we can select the curve that most closely matches system conditions at the time of the fault. The ratio of 0.27 corresponds to a line length of about 75 miles. Thus, we conclude that the trouble spot is approximately 75 miles along the line from station A to station B. In this particular case, a foot patrol located the probable tree contact within a mile of the calculated distance. The problem of recurring tripping of the line was solved by tree trimming. Incidentally, some utilities use fault locators which are programmed to perform the calculations and then give us the exact distance to the fault. Okay, in this segment we have shown a couple of examples of how valuable oscillograms can be in a fault investigation. In the next two segments, we'll consider some actual case histories of faults and how they were investigated. At this time, switch off the videotape, study this material in your workbook. Hello again. In previous segments, we introduced you to the basic tools and techniques used in fault analysis. And now, let's tie all this information together by looking at some real-life case histories. We've already examined a case where a line tripped out of service and reclosed successfully. Now let's consider case 1, an unsuccessful line reclosure. In practice, this happens quite frequently when the line does not stay de-energized long enough for a temporary fault to clear on its own. In this example, the oscillograph has captured the substation bus voltages in all three phases, the transformer neutral current, and line current for one of the transmission lines. The oscillograph system in use here can record 3 cycles of pre-fault data. From the trace of line current, you can see that the line we have monitored is not the faulted line. This is obvious since the current resumes its normal load level after the fault is cleared. From the bus voltages, we conclude that the fault is a single line-to-ground fault on A phase. This is confirmed by the transformer neutral current. We can also tell that the fault duration is 4 cycles, and the line dead time is 11 cycles. At this point, the breakers on the faulted line reclosed, but the fault was still there. So the breakers immediately tripped out again and locked out. If this problem repeats itself over a period of time, we may conclude that 11 cycles of dead time is not enough to allow the temporary fault to deionize and dissipate. In this case, the dead time would be increased by changing the time delay at the breaker. Our next case history, case 2, shows what happens when the nature of the fault itself changes during the disturbance. Here we have a fairly extensive 69 kV subtransmission system that experiences a fault on the tie line between substations Y and Z. The 69 kV system is delta connected, but effectively grounded through zigzag grounding transformers located at substation X. Notice that all the oscillograph equipment is installed in substation X, remote from the fault location. In spite of this distance, we can still obtain a great deal of information from the recordings. The oscillograph has recorded 69 kV bus voltages in all 3 phases, neutral current in a grounding transformer, and current in the bus tie breaker, all 3 phases as well as the residual current. The total elapsed time between the initial fault and final breaker clearing was 65 cycles, just over 1 second. Notice that we have broken the traces to indicate where the waveforms just repeat themselves. After 3 cycles of pre-fault recording, we see the onset of a single line-to-ground fault. This fault was actually caused by a tree falling across one of the phase conductors. The tree provides a path to ground. Looking at the oscillogram, the transformer neutral current and the tie breaker residual current both clearly show that the fault is line to ground. The high C-phase current in the tie breaker and the low C-phase bus voltage tell us which phase has been faulted. The single line-to-ground fault endures for 25 cycles. At this point, the C-phase conductor burns open, allowing the tree to fall onto A phase. However, the tree still maintains contact with C phase. Now, the nature of the fault has changed to a double line-to-ground fault. Over the next 5 cycles, you can see the effect of the 2-phase fault. Both A phase and C phase currents in the tie breaker rise sharply. Both A phase and C phase bus voltages are depressed. Transformer neutral current and tie breaker residual current are both still present, but they are reduced in magnitude. This is because a double line-to-ground fault is more balanced than a single line-to-ground fault. At this point, breaker Y finally trips to clear one end of the faulted line. The tripping occurs 30 cycles after the initial line-to-ground fault started. This is reasonable since we are dealing with a high impedance fault. Thus, the level of fault current is low, resulting in a relatively long operating time. For the next 25 cycles, we still have a double line-to-ground fault, but the current magnitudes are very much reduced because one end of the line is open. You can see that the A and C phase bus voltages are back to near normal. At this point, the fault again changes. The A phase conductor now burns open. The tree contacts B phase and falls to the ground. But all three open conductors are now in contact with ground, resulting in a three-phase-to-ground fault. For the next 10 cycles, we have a balanced three-phase fault. You can see this from the three fault currents in the tiebreaker and the fact that neutral and residual currents are now zero. Breaker Z at the other end of the faulted line now trips to completely clear the fault. This occurs 35 cycles after breaker Y trips. Again, this is reasonable because the fault current is low and also because the fault is in zone 2 of breaker Z's protection. Thus, tripping is further delayed. This example has demonstrated two things. First, the nature of a fault can change during a disturbance, and in this case, the protection operated correctly to clear the fault. Secondly, our example showed that recording equipment located several buses away from the actual fault can still provide valuable information during a fault investigation. Let's now move on to our third case, an overtrip for a remote fault. This is a clear example of misoperation. Breaker A at 115 kV substation Z trips for a remote fault on the 230 kV system. With the help of the oscillographs located in substation X, we were able to spot the problem and correct it. In substation X, the oscillograms monitor the transformer breaker's A-phase current and the zero sequence residual current. Also monitored are the 115 kV bus voltages in all three phases, as well as A-phase and residual current for breaker B connecting to substation Z. You can see the onset of a single line-to-ground fault on the 230 kV line. The fault was on A-phase, as shown by the sharp increase in A-phase current through the transformer breaker and breaker B, and also by the depressed A-phase bus voltage. The presence of zero sequence in the breakers also indicates a ground fault. Tripping on the 230 kV system was correct, and the fault was cleared in just over 3 cycles. But look at the phase current through breaker B. Normal load current flows after the 230 kV fault clears, but 5 cycles later, breaker A trips at the remote end of the line. The incoming feed from substation Z is now interrupted. After 14 cycles, breaker A recloses and remains closed. Further investigation revealed that while the fault was on, breaker A received the proper carrier blocking signal. But this signal was removed too quickly. As a result, the relays at breaker A saw fault current as well as a green light to trip. The problem was solved by resetting the timing of the carrier block signals. Again, this is a case where the overtrip problem may have gone unnoticed if we had not checked the oscillograms. Okay, let's take a break now, and then we'll come back and describe some more examples. In the meantime, switch off the videotape and review your written materials. Hello. In this last segment, we'll examine some additional oscillograms from actual case histories. These cases demonstrate how recordings can be used to assess the performance of major system equipment, such as circuit breakers, transformers, and generators. Let's begin with Case 4, a breaker restrike. By way of review, you know that when a circuit breaker opens to interrupt current, an arc is formed between the parting contacts. Normally, this arc is quickly extinguished by the dielectric in the interrupting chamber, which may be air, gas, oil, or vacuum. After the arc is extinguished, there is voltage buildup across the open contacts. If this voltage builds up too fast, or if there is a sudden surge of voltage, the dielectric strength of the breaker's insulation could be exceeded. When this happens, the arc is reestablished and current again flows. This dielectric breakdown is known as a restrike. It can cause serious damage to the breaker contacts, in addition to deterioration of the oil or gas dielectric. But how can this happen? Well, here's one way. A lightning strike to a phase conductor flashes over an insulator, causing a single line-to-ground fault. The breaker at the substation successfully clears the fault, but a very short time later, perhaps a few cycles, there is a second strike to the line. The resulting surge in voltage causes the open breaker contacts to restrike. But in only a few cycles, the ionized gases from the original fault have not had enough time to dissipate. So the original fault reestablishes itself. Usually, the fault current will go out at the next current zero after a half cycle. Here's a set of oscillogram traces showing an actual restrike on a 500 kV air blast circuit breaker. The initial fault was on B phase to ground, and it successfully cleared after 7 cycles. About 1 cycle later, lightning struck C phase conductor, causing the breaker to restrike. In this instance, the original B phase fault was not reestablished, but a different fault occurred on C phase. Thus, the lightning strike caused both a restrike and a fault. The C phase fault current was extinguished 1/2 cycle later. Notice that the fault on C phase was more than double the magnitude of the initial B phase fault. Well, so much for breaker restrikes. We've seen how oscillogram recordings can be quite useful in spotting this type of breaker performance. Now, let's consider case number 5, generator instability. We've already mentioned that unlike a fault that is cleared in a few cycles, instability may last for several hundred cycles. This is on the order of several seconds. But like a fault, the effects of instability can be captured on an oscillograph for future analysis. As you know, instability can occur when the rotors on the synchronous machine speed up or slow down in response to some disturbance. The disturbance can be a fault, loss of a generator or line, or a load change. This acceleration and deceleration of the rotor causes natural oscillations on the system that usually die out in time. Consider, for example, the loss of a generator on this power system. This trace shows megawatt flow into the area. The inflow immediately increases to supply the loss. But before the remaining generators settle down to their increased megawatt outputs, you can clearly see some oscillations. Most oscillations like these are well damped and die out in a few seconds. However, sometimes the oscillations actually grow in magnitude with time. You will remember that we discussed this problem of instability in an earlier tape. When instability occurs, we will see oscillations not just in megawatt flow, but also in voltage, current, megabars, and system frequency. Oscillations in voltage and current show up as envelopes superimposed on the normal 50 or 60 hertz voltage or current. This example shows generator terminal voltage and stator current recorded on a conventional fault recorder in the power plant. In this case, the unit lost synchronism and began slipping poles after a major tie line was opened. The recording shows about 1 second of the disturbance. At this point, the generator trips offline. You can see that oscillogram recordings such as these are quite valuable to engineers and others concerned with investigating a disturbance. They provide us with documented evidence of the disturbance and allow us to determine if the protection has operated as planned. Let's now move on to our final case study, case 6, transformer energization. Here, we'll show how an oscillogram analysis can help improve switching procedures for system dispatchers. We're considering 2 different switching procedures for energizing this 500 kV, 230 kV transformer. In the first procedure, breaker C is closed to energize the transformer, with breaker D at the remote terminal open. In the second procedure, breaker D is closed first before energizing the transformer with breaker C. The oscillograph has recorded voltages and currents on the line side of breaker B at the transformer substation. Here we show the traces for procedure 1 with breaker D open. This looks quite strange. Voltage VA on the A phase shows some distortion, also VC to a lesser extent. And this current IA must represent transformer magnetizing current. Your workbook explains why only one phase is affected. First, recognize that we have 150 miles of open 500 kV line. This means that the voltage at the very end of the line at breaker D will be quite high due to the capacitive line charging. That is, the Ferranti effect. This voltage was measured to be 567 kV. In fact, there is a voltage rise all along the length of the line. At the transformer substation, the voltage is also quite high, 560 kV. The moment breaker C closes, this high voltage is applied to the transformer, forcing it into saturation. This results in a very large magnetizing current flowing into the unloaded transformer. As you know, this magnetizing current is distorted and unbalanced. This causes distorted voltages at the transformer that may very well stress the transformer insulation enough to cause a failure. The second switching procedure shows the effect of closing breaker D before energizing the transformer. Now we have normal load current flowing along the line before the transformer is energized. Since there is no longer an open-ended line, voltage at the substation bus is about 10% lower than when breaker D was open. Now, when breaker C closes, there is still distorted magnetizing current flowing, but it is much smaller in magnitude. This is because the voltage impressed on the transformer is much lower. In fact, you cannot even see the magnetizing current on the oscillogram because it is very small and superimposed on the normal load current. But you can see that the transformer voltage is now much less distorted, so the insulation is less stressed. Our lesson here is quite simple. Transformers should not be energized from long, open-ended lines, especially high voltage lines. The proper switching procedure is procedure 2. Close breaker D before energizing the transformer. Okay, so we've now reached the end of our lesson on fault investigation and analysis. Our objective was not to make you an expert in interpreting oscillograms. Rather, we've given you a general overview of why fault investigation is important and how oscillograms and other tools can be used to understand and solve a variety of problems on the power system. Please switch off the videotape at this time and go through this material in your workbook.